How's everybody doing out there? This is sort of strange times that we're in now, but we're going to try to do some lectures online for the remainder of the semester. I kind of wanted to talk with you today and walk you through a couple of things related to how the course is going, some of the announcements I've made, and then we'll take a look at some lecture notes. We're going to talk about the Robin problem today. So these are the lecture notes for Monday, March 23rd. I'm recording these on Friday, so they'll be up this weekend most likely, and you'll get a chance to start looking at some material. A couple of things that you'll notice if you go to the Canvas page is on the front page where the office hours used to be, I have an invitation to virtual office hours. I'll be holding virtual office hours from 1 to 3 p.m. Monday through Thursday, starting this next Monday. To access those virtual office hours, you simply click on this link, and it'll send you to what's called a waiting room, which essentially it's sort of this digital waiting room, and it lets me take one student at a time and pull them into an online chat session. It'll be a video chat session as well, so you're welcome to have headphones, microphone, webcam, whatever, and we can chat about homework or life or anything else that you want to chat about. But I will have virtual office hours from 1 to 3 p.m. starting next Monday. A couple of announcements that have been made that I want to make you aware of. The first announcement here is that the virtual office hours do begin this next week. We just talked about that. Textbook availability. If you do not have a textbook with you, or if you don't have it, or you're unsure of where it is, please respond to this. I see a couple of you have already responded. I need to know who has their textbook and who doesn't. If everyone has their textbook, great, but if some people don't, then I will try to make some photocopies available for everyone online to take a look at. Let's see, other announcements. Talked about scanning and submitting work. So starting this next week, we will have a quiz due on Friday and homework due, I believe, on Sunday is the way I have it set up. Let me go in and take a look at that real quick. Let's see. Yeah, homework's going to be set up on Sunday. So the way this is going to work is each week you'll have a quiz due on Friday, and then the homework for that week will be due Sunday. Both of these will be due at 11:59 p.m. Basically what you'll do is you'll simply print off a copy of the quiz or a copy of the homework, work it out like you normally would, and then scan it and upload it to Canvas, and that way I can just grade the PDF copy with my own annotations, just like I'm grading an actual physical copy. I can do that all online and grade them that way so that you have good feedback. That's kind of what I'm looking at here for the rest of the course as we go through this cycle of one quiz per week, one homework set per week, and then we have the project at the very end. I'll give you more information about your projects. For sure, we're going to have some sort of research paper kind of thing going on with those. We'll see whether or not I'm going to mix in a presentation or not as we get a little bit closer to that time. The one thing to know about your presentations, make sure, or your projects, make sure that you've gone in and uploaded the literature review before we get back into the swing of things this next Monday. So go in and take care of that before spring break is over with. Other than that, I think we're mostly ready to go. So what we're going to do for lectures is I'm going to work through notes with you just like I would do in class. And the benefit of this is these notes will be available to you online in video form and in note form. I'll upload the written notes as well for you to take a look at. And this corresponds directly to what we would have done in learning catalytics. So hopefully this will be a good thing for a lot of you. It'll let you get my interpretation of some of the things that we're doing in class in a nice video form. And there will also be videos available like we've normally had. Those videos will be available in Canvas in the places where they've normally been. In fact, if you look at Canvas real quick, you can see that we are finishing up section 2.5 today, which is on Robin boundary conditions, and then we'll start section 2.6 on Wednesday, and you can see I already have the material for section 2.6 up. So we'll talk more about that a little bit on Wednesday. But for today, we're going to look at the Robin boundary condition. So the Robin boundary condition, if you recall, so it's just a simple example of it here. I have a thin metal rod that's conducting heat. It's of unit length, so it's length 1. So let's say that this is x equal to 0. This is x equal to 1. At the left endpoint, my temperature is held at 0 degrees. At my right endpoint, you can imagine that this metal end is submersed in some sort of gel or liquid, and the temperature of the liquid is held at 0 degrees. The difference between these two conditions, we know that this is a Dirichlet condition on this side, whereas on this side, this is what we call a Robin condition. And the main difference in the two conditions is in the Dirichlet, the temperature is held fixed at that left endpoint, whereas in the Robin condition at the right end, you do get heat flow happening between the two according to Newton's law of cooling. So what that looks like in the case where you have a 0 degree temperature is this condition right here. That's the Robin condition for this problem. And that's going to be the new thing that we haven't tackled yet. So we're going to look at how to handle Robin conditions, or mixed. Sometimes we call them mixed boundary conditions because they have both flow and state specified at the right-hand sides. So sometimes we call those mixed boundary conditions. But we're going to talk about the Robin boundary condition on the right end. We assume the temperature of the rod is given to us initially by this temperature profile, and we're actually going to use Maple to do a fair bit of this here in a little bit. But we want to start where we've started up till now, and that is separating variables. So we're going to suppose that u of xt is x of x times t of t. We're going to substitute it in to the heat equation. We've done this countless times so far. And so we have x times t prime is equal to k x double prime times t. If we separate variables, we get t prime over kt is x double prime over x, and we'll use our familiar separation constant of negative lambda. So we end up with two problems here. The eigenvalue problem is x double prime plus lambda x equal to 0. And the time problem is t prime plus lambda kt equal to 0. And we're familiar with the solution of the time problem at this point. We know that the solution of the time problem will be e to the minus lambda kt. So we know that that is a decaying exponential in this case. We also know the eigenvalue problem if our boundary conditions are Dirichlet or Neumann or mixed Dirichlet and Neumann. We've handled all of those. Remember, we had that table of different eigenvalues and eigenfunctions for all those different mixed conditions. But here we have a Robin condition. So I don't know the solution to this eigenvalue problem as is. In fact, the boundary conditions are a little bit different here. You can see the two boundary conditions here and here. The first boundary condition simply states that x at 0 will be 0. And I want to look at the second one a little bit more closely. The second one says u sub x of 1t plus u of 1t is 0. So if u of xt is x times t, then this implies that x prime at 1 times t of t plus x at 1 times t of t is 0, which is another way of saying x prime of 1 plus x at 1, pulling out the t of t term here, that is equal to 0. So you have a choice here that either this term is 0, which would make the time problem 0 for all time, or what we are going to then assume is that x prime at 1 plus x at 1 equals 0. So that's the boundary condition, the new boundary condition for us. This is the Robin eigenvalue condition. It's a Robin eigenvalue condition. It just so happens to be a non-homogeneous condition because the rod was submerged in a 0-degree liquid. That's why this term is 0. So it is a homogeneous condition. We're going to study inhomogeneous conditions the rest of this week. So we've got our eigenvalue problem, we've got our time problem. The question is, how do we solve for our eigenvalues? So let's do that on the next page here. So let me copy down my eigenvalue problem real quick. Okay, so we have cases. We can't just rely on a table here because this is a new type of boundary condition for us. We don't know the solution to this eigenvalue problem from memory. So we do have cases. I'm going to consider two cases. The first case that we have is that lambda could be 0, in which case we're looking at x double prime equal to 0 for our ODE here. And so the solution x of x will be some a x plus b. And the first condition, x at 0, implies that b is 0. And the second condition, x prime at 1 plus x of 1, that would be, let's see, x prime is a, plus x at 1 is a plus b. Right, so x prime at 1 would be a, plus x at 1 would be a plus b, but we know from this condition that b is 0. So it looks like this gives me 2a, which also has to be 0, because x prime at 1 plus x at 1 is 0. So this implies that a is 0. So there are no eigenvalues which correspond to lambda equal to 0. All right. What we need to take a look at now is a case other than lambda equal to 0. And what I'll say about this is there are two possible cases here. Lambda could be positive or lambda could be negative. So if we look at x double prime plus lambda x equal to 0, we know that the characteristic equation is r squared plus lambda, so that the roots are plus or minus the square root of negative lambda. So those are our roots. We know that we will get oscillations, which are actually going to yield those are what are going to yield our eigenvalues. If you don't have sine and cosine, if you have sinh and cosh instead, we've shown multiple times in class that that case does not give eigenvalues. We're actually going to prove that here in about 2 weeks or so. But as it stands right now, we have to consider the case where there's oscillations, because that's the case that will give us eigenvalues. So oscillations occur so long as lambda is in fact greater than 0, because we want this term to be negative. We want it to give us complex numbers. So we need lambda to be greater than 0. If that's the case, then usually what we'll do is write it this way. So these are what our characteristic roots are. Do it this way. So these are our characteristic roots. We know that these correspond to oscillations involving sine and cosine. So the case that we're in is we're in the case lambda greater than 0 here. So under that case, our solution for the eigenfunction would be some combination. I'll say a cosine square root lambda x plus b sine square root lambda x. Our first condition, x of 0 is 0. Let's see, x of 0 is just going to give us a, so that forces a to be 0, which is nice. So you know that this is equal to 0. So our next condition, let's look at x prime of 1 plus x of 1. So x prime at 1 is, so you're looking at this sine term. When you take the derivative, you will get b square root lambda cosine. These are evaluated at 1, not evaluated at 0, so I can't just dismiss it altogether. So evaluating it at 1, you'd get square root of lambda here. Plus x at 1, you would get b sine square root lambda. And so this equals 0. So what we have here is b square root lambda cosine square root lambda plus sine square root lambda is 0. Well, I don't want to have a trivial solution here since this is an eigenvalue problem. We're looking for non-trivial solutions. So b cannot be 0. So what must happen here is we must have square root lambda cosine square root lambda. That must equal, well, minus that must equal sine square root lambda. Or another way of writing that is minus square root lambda equal tangent square root lambda. Or another way of saying that is the eigenvalues lambda n are equal to the square root of the nth root of the equation tangent x equal negative x. So in other words, the first positive, so lambda 1 is the first positive root, because remember lambda is greater than 0 here. The first positive root of the equation tan x equal negative x. Actually, let me just write it this way. First positive root of tangent x equal negative x. And so lambda 2 would be the second positive root of this equation. And so on. And here's the problem. There is no formula for this. There is no explicit formula to determine lambda n as a function of n. Which means that I'm going to have to numerically calculate these. So the upshot of all this is we must numerically calculate these eigenvalues in Maple. So there's a reason why the Robin problem isn't in that table of eigenvalue problems in your textbook. All of those eigenvalue problems in your textbook have explicit formulas for the eigenvalues, and no such formula can be found here. So this is a problem type, these Robin problem types, where you have to use Maple or some sort of computer algebra system to determine the eigenvalues. So I'm going to walk you through that process here in just a second. But now that we know that we can find the eigenvalues, I do want to talk quickly about what the solution would look like, including the coefficients, and then we'll wrap it all up in Maple. So just to kind of backtrack and make sure we understand where we are at this point, We know that that term is 0. We know this term we keep. This term then becomes the eigenfunction. And I don't need to keep the constant because remember I'm going to take a linear combination of all my eigenfunctions. So I'm just going to take the sign. So we'll say that xn of x is sine square root lambda n x. So if I come over here, what I know at this point is I've got my eigenfunctions. They are xn equals sine square root lambda n x. I've got my eigenvalues. They are lambda n equal the nth root of the function tangent x equal negative x. Both of these are for n equal to 1, 2, and so on based on the way we indexed it. Because remember, this is the n equal to 1 would be the first root of this, n equal to 2 would be the second root, and so on. We don't start with n equal to 0, the 0th root, because lambda equal to 0 was not an eigenvalue here. If lambda equal to 0 was an eigenvalue, then we would start with that. Which is why, even though x equal to 0 satisfies this equation, because tangent at 0 is 0, we don't use that because that would imply that lambda equal to 0 is an eigenvalue, which it's not. So this is really only valid for n equal to 1, 2, and so on, or if you wanted to maybe write it in terms of x, it's only valid for positive x. I'm only looking at the positive roots of that equation. Then we know our time problem as well. We know that the time problem solution Tn of t is e to the minus lambda n kt. And yeah, so that's where we are, which means that we call this the product solution. So the product solution u sub n of xt is it's of the form xn times tn. And so our general solution is the set of all linear combinations of the product solutions. So I'll write Cn, Xn, Tn. And we know what each of these are, right? We know what Xn is, we know what Tn is. What we don't know at this point is what Cn is. So our goal now is we need to find a formula for Cn. And that's where the initial condition comes into play. If you look back at the original problem, we've yet to use this term. So we're going to do that now. So u of x0 is x times 1 minus x, which implies that x times 1 minus x equals the sum. N goes from 1 to infinity of Cn xn, and since this is at t equal to 0, this will be Tn of 0, but if you look at the time problem, Tn of 0 is, well, just 1. So this is giving me what we call a Fourier sine series, except it's not exactly a Fourier sine series. We'll talk about why. The eigenvalue, or the eigenfunction here, is sine square root lambda n x. Now here's the thing. This is what we call a generalized Fourier series. The reason it is not a Fourier sine series is because the eigenvalues here are numerical. They're not the n pi over L that we've been used to, or the 2n minus 1 halves pi over L that we've been used to. These are the numerically calculated eigenvalues. So this is our generalized Fourier series for this problem. In order to figure out the CNs, we're going to do a very similar thing to what we've been doing so far. We're going to take both sides of that equation and multiply by another member of that set. So take another eigenvalue, take the mth root of that equation, and we're going to multiply both sides by a different eigenfunction. Okay, then I'm going to integrate over the interval, which is from 0 to 1. So if I integrate 0 to 1 on the left-hand side, and I integrate 0 to 1 on the right-hand side, I can actually bring my integral inside the sum all the way up until I encounter a function of x. So we have this, and at this point it's a question of whether or not these are orthogonal. And it's actually a pretty hard thing to prove, but it does turn out that these are orthogonal. We're actually going to prove that here in just a little bit. So since those are orthogonal, what we know about this is the only case where these give me something other than zero is when n equal to m. That's the only term that survives. It's the only term that survives the sum. Because when n is not equal to m, this thing is equal to 0. So the only term which survives is the following. I'm going to set m equal to n, so this will be sine square root lambda n x. Over here, all of the sums, the only sum that matters is when n is equal to m. That's the only term that matters. And so in that case, we're going to have cn, or cm, depending on how you want to look at it, and we're going to get two of the same signs. So both of them are going to be lambda sub n's. So this would be the integral from 0 to 1 of sine squared square root lambda nx dx. That's the only term that survives, is when lambda n and lambda m are equal to each other. And here's the problem. We've gotten used to being able to say that this term is half of the interval length. So up till now we've been writing that integral as 1/2, but that is only valid for the sine n pi x over L, which this is not. So I can't tell you what that value is. This is also going to be numerically calculated. As the eigenvalue is numerically calculated, so too will the coefficients Cn be. So putting all this together, then, our final formula here is the coefficients Cn are the integral from 0 to 1 divided by the integral from 0 to 1, like so. And using our notation for inner product, remember that this is the original initial condition here. It's probably good that you think of writing it this way. And this is where the inner product of f of x and g of x is defined as the integral from 0 to 1 of f of x, g of x, dx, right? So this is the inner product on the set of continuous functions on the interval from 0 to 1. So this is the form that the coefficients take, and we're going to figure out pretty soon that, well, that's the form that they always take. Even if we can't write a nice formula, we know exactly what they're going to be in terms of the inner product. So these are what are called the generalized Fourier coefficients. All right, so let's see if we can hop over into Maple and figure out what these values are and come up with some answers. So let me put this over here. We'll grab Maple real quick. Here's the problem that we've been looking at. Let's see, make this a little bit bigger too. All right, so what I'd like to do, I'd like to insert page. All right, there we go. So let's keep going here. I want to write down my solution. So I want to know what is the solution, and let's just do the first, let's see, how many terms did I do over here? 1, 2, 3, 4. I did the first 6 terms. So let's do the solution, u of xt. Sum n goes from 1 to 6 of cn xn tn. So we're going to do the first 6 numerically calculated terms. Now, this is obviously an approximation. We hope it's an approximation to the solution that gives us good error. We want the error to be small, and in fact, the error is pretty small here. As the number of terms calculated goes to infinity, obviously the error goes to 0. Now, that's something we would need to prove. That is a consequence of some of the stuff we're going to look at when we talk about 4A series coming up soon. But in terms of this problem, let's go back to where I said we needed to calculate the eigenvalues. So we need to calculate the roots of this equation to give us the eigenvalues. You can see here in this graph, I have the graph of tangent and negative x, and so wherever these graphs intersect, remember we don't include x equal to 0 here, wherever these points intersect, these are our eigenvalues. So there's our first eigenvalue, there's our second eigenvalue, there's our third eigenvalue, and I should really say, I should really be careful about this because it's not, so back up where I had this, the square root of the eigenvalues, right? The square root of the eigenvalues are the nth roots of this equation. So the square roots are these intersections, right? So if I square that number, that's the first eigenvalue. Well, the easiest way to find those eigenvalues is through the fsolve command. So I just, this is the same thing as tangent x equal to negative x. So I'm solving between, say, 1 and 3. I'm looking for that intersection point. So the first thing related to the eigenvalue, remember the eigenvalue is technically the square of this number. So this is the first root of this equation. This is the second root, the third positive root, the fourth positive root, fifth, and sixth. So you've got first, second, third, fourth, fifth, sixth. Those numbers are these numbers right here. We know that I'm going to need to store those numbers somehow. So I called it evals. Remember, this is technically the square. These numbers are technically the square root of the eigenvalues. But I just called them evals, and I stored these 6 numbers to an array or a list here in Maple. You'll see why that's beneficial here in a little bit. And then I created a function for the coefficients. So the coefficient formula that we had over here, if you'll recall, this is what our coefficient formula looked like right here. And I've got that same coefficient formula in right here. This is also a place, by the way, where you can save yourself a little bit of computation time by using the option numeric as well. So if you want to use the option numeric, it does a numeric calculation of the integral, and it's actually it's faster to produce those values. So here's the really key step. I want to know what each of these coefficients is at different values, right? So what I want to do is evaluate this formula at each of these lambdas that are given by the square roots, right? So it's really square root of lambda, which are these numbers here. So all I've done is I've plugged each of these numbers in for lambda and computed this integral and stored that value here. So this is C1, this is C2, C3, C4, C5, and C6. I'm just calculating numerically each of the coefficients. All right, if I continue with that, then this is what my general solution, or not general solution, the first 6 terms looks like. It's a sum of the coefficients times this would be the time problem. Notice on the time problem, it's lambda kt, not square root of lambda t. So I've got to take those numbers I had above and square them to get lambda rather than the square root of lambda. And then sine square root lambda x. And so there's what my solution looks like. So, what I'm asking you to do here ultimately is tell me something like the following for the answer. I'm asking you to tell me, okay, u of xt is 0.21328 e to the minus 4.1158 sine 2.028757 plus, and then list all of the terms, right? So, the next one would be 0.10404. So in your homework for a Robin problem, this is what I'm looking for as your answer. I'm looking for the first several terms of the sum listed out. And Maple can help you with that, and you have access to this Maple file to take a look at if you get lost on it or need to go back and take a look at it. So you can see here, once I've calculated, or once I have written my u of xt down, I can then plot it. So that's the importance of this step right here, is writing it down so that you can plot. Basically, you're plotting this thing, so you can plot that function. And I'm doing it at, remember the heat problems diffuse very, very quickly. So I'm looking at this in 25 thousandths of a second intervals. So I'm looking over the first 40 of those, just so I can see kind of the behaviors. So the original heat distribution is just a parabola. So it's just this kind of parabola. And you can see after 1/25,000th of a second, it starts to bend like this. And then these are the terms. Like long term, what should be happening if your rod is held at 0 degrees on the left. So this side is held at 0 degrees. And on this side, it's immersed in a liquid that's 0 degrees. And it's exchanging heat back and forth. Then eventually, the whole rod will be 0 degrees in temperature. And you can see that's what's happening. The temperature profiles are getting closer and closer to 0 degrees here. More interestingly, what I want you to look at is, do you notice how all of the slopes at the right end are all negative? Remember our boundary condition over here is ux of 1t plus u of 1t equals 0. Which another way of saying that is ux of 1t is negative u of 1t. So the slope over here, so this is the slope at the right end, is the negative of the temperature. Which you can see that. So you can see the Robin condition being satisfied over here. The steeper the slope, right, the higher the temperature, and as the temperature goes down, you see the slopes get closer to flattening out. And it is Dirichlet on the left end because all of the points are collected at, or fixed at, 0 degrees on the left end. Here's a 3D map of those time snapshots over time. So you've got the initial temperature profile here, and over time it decays down to 0 because of the time problem being a decaying exponential. But this is the Robin problem. It tells me how the heat distributions are going to change over time over the length of this rod. All right, so that being our Robin problem, I'm only really going to do one example of it because all the examples are very similar. You're going to do several different things like this where you go in and calculate the eigenvalues numerically. What I'd like to do at this point is make sure that we understand some of the lessons that we've learned from separation of variables so far. So here are the lessons that we should kind of know at this point. The family of eigenfunctions. This is our base family, right? This is the base Dirichlet or Neumann families. Those families form an orthogonal family on the interval from 0 to L, which means that this integral from 0 to L of any two members of that eigenfunction set are equal to 0 when they don't equal to each other. You can also say the same things for cosine, so I guess I should have written the Neumann down here. If it's Dirichlet, you get that. If it's Neumann, you get this. And we didn't look at it, but if you have periodic conditions, you get what's called the full Fourier series set. So we get three sets of orthogonal families. And one of the things that I haven't talked about very much, and kind of starting here is where this talk begins. This is a definition that I don't know if it's worth memorizing, but you should at least be aware of it. This is the definition of all the different kinds of boundary conditions we're looking at, and then an extra condition. And it's this extra condition that I want to make sure you're aware of. If this condition is met, the boundary conditions are called symmetric. So all of our boundary conditions so far are like these. You can see here, so what would a Dirichlet condition be, right? A Dirichlet condition would be x of 0 equal 0. So what is that? Well, that's just say alpha 1 is 1, x, let's let a be 0, right? So this is x of 0. And then just make that coefficient 0, that coefficient 0, that coefficient 0, and voila, you have a Dirichlet condition at 0. You can see the Neumann conditions are in there because you've got the derivatives in there. And because the derivatives and x, because both x and its derivative are in there at a point, then you have Robin conditions as well. So every boundary condition we've talked about so far in the course is like these boundary conditions for different values, different constants, alpha 1, beta 1, gamma 1, delta 1, etc. If eigenfunctions also, if you take any two eigenfunctions from your set and your eigenfunctions also satisfy this additional condition, then it's known as a symmetric boundary condition. Symmetric boundary conditions have very nice properties. The fact is, every boundary condition we've looked at so far, they're all symmetric boundary conditions. And if you know you're working with symmetric boundary conditions, then you have access to these four things, which you can always say. So if you have a symmetric boundary condition, you always have an orthogonal family. So when we were working on the Robin problem, I said, oh, look, we have orthogonality. So right here where I said these are orthogonal, that's because of this theorem. That's because the Robin boundary condition is a symmetric boundary condition. Therefore, by this theorem, the eigenfunctions which are created form an orthogonal family. We're going to prove that, by the way, here in just a second. The other thing you know, if you want to find the coefficients, this is how you do it. So this is the formula for the coefficients. We just did that. If you go back up and look, it's the exact formula that we have right here. So this is the exact same formula. This is where the function f of x, that initial condition is x1 minus x, and this is xn, the eigenfunction. So you have the inner product of f of x with xn. So if you look, the inner product of f of x with xn over the inner product of the eigenfunction with itself. That's always going to be the formula for the coefficients, regardless of whether or not you have to numerically calculate the eigenvalues or not. If you have symmetric boundary conditions, that's what they will always be. You will never get complex eigenvalues. Now, that's not to say you won't get complex eigenvalues. You will, but if you remember how we handled this in ODE, we took the real and imaginary parts of those which are real. And the same thing happens here. If you have symmetric boundary conditions, you're guaranteed to not have any purely complex eigenvalues. You can always take the eigenvalues and corresponding eigenfunctions and make them real by taking the real and imaginary parts. We're not going to prove that in this course, but it is a true statement. We will prove statement number 4 a little bit further down the road. Notice we've been ignoring the case where lambda is less than 0. We can continue to ignore that case because if you have some symmetric boundary conditions, those will never yield eigenvalues because all of our conditions that we've looked at have satisfied this extra condition. We'll actually prove this later. We'll prove this in general later in the course. So what I want to do is actually prove 2 of the things that we've been relying on quite heavily, and that is 1 and 2. We're actually going to prove those today, and that'll be the last thing we do in this lecture. So I'm going to start with a proof of number 1. So I'm going to start with a proof that the eigenfunctions form an orthogonal set if you have symmetric boundary conditions. So I want to suppose that x double prime plus lambda x equals 0 has symmetric boundary conditions. This is the eigenvalue problem that we've been looking at all along. So I want to let lambda 1 and lambda 2 correspond to eigenfunctions x1 and x2. Then it's the case that, let's see here, minus x1 double prime equals lambda 1 x1 and minus x2 double prime equals lambda 2 x2. All this is, by the way, and this is for lambda 1 not equal to lambda 2. We're assuming that we have 2 different eigenvalues with their associated eigenfunctions. If they satisfy this equation, then that means x double prime is minus lambda x, and I've just shifted the negative over. So that just says that these satisfy this equation. All right, so by the product rule, and this is the key realization for this proof, by the product rule, you must have minus x1 double prime x2 plus x1 x2 double prime. That quantity can be shown to be the same as this quantity. Now I know you may be thinking, what would possess such a person to look at this kind of quantity? So if you take the derivative of this term using product rule, you'll get this term. Encourage you to work that out for yourself. But why did we think to look at this? Well, we thought to look at this because if you go back and look at the condition for symmetry, right here, this condition, if we replace that with x1, it's x1 prime, x2, minus x1, x2 prime. That evaluated from a to b equals 0. That's what it means to be symmetric. So if you have two eigenfunctions from a set of eigenfunctions and they're symmetric boundary conditions, then you know the eigenfunctions have this relationship. So if I multiply both sides of this by a negative, we get this relationship. And if you look at this thing right here, this is exactly what I have written down below. So this is that exact thing, which means, nicely enough, if I take the integral from a to b of both sides of this, the integral of a derivative, those cancel out, but you still have to evaluate this from a to b. We know that this thing is equal to 0 because we have symmetric boundary conditions. So if the thing on the right-hand side is equal to 0, that means the thing on the left-hand side must also be equal to 0, since this is an equation. And what you notice on the left-hand side is that this is the integral from a to b of, if you pull out, let's see here. Replace them, right? So take this and replace negative x1 double prime. Then you'll have lambda 1, x1, x2. And here you'll have x1 replace x2 double prime with negative lambda 2. So make this negative. You know that that's equal to 0. But what is really interesting here is that you can pull out the x1 and the x2, and then all you have left is lambda 1 minus lambda 2, and you know that quantity must be 0. So what does that imply? Well, if lambda 1 doesn't equal lambda 2, remember I supposed that up here. We're supposing that those two aren't equal to each other. Then either that term is 0, which can't happen, or must be that this term is 0. So therefore, the integral from a to b of x1, x2 dx equals 0, or x1 is orthogonal to x2. And keep in mind that we arbitrarily chose the two eigenfunctions from the set. So if you have symmetric boundary conditions and you choose any two different eigenfunctions, this proof shows that those eigenfunctions are in fact orthogonal. So we have mutually orthogonal sets of eigenfunctions. It's a really cool proof. Second proof we've basically already done today. I'm going to still do it with you anyway. We've basically already showed this is how you find the coefficients. So we have to suppose that our function, this is called square integrable. We have to suppose that we're not dividing by infinity, basically. We have to show that our function is square integrable, but if it is, then we can expand our initial conditions in terms of the eigenfunctions, and when we do this this is called an eigenfunction expansion. And when we do the eigenfunction expansion, the coefficients can be found with this formula. So let's take a look at that real quick. The proof for this is quite easy. Suppose that f of x equals the sum and goes from 1 to infinity of cn xn, where xn are eigenfunctions of a BVP with symmetric boundary conditions. In particular, if you look at the theorem here, it's this boundary value problem, right? So it's not just any BVP, it's that boundary value problem in particular. It's x double prime plus lambda x equal to 0. So suppose we're solving that problem, that eigenvalue problem, with symmetric boundary conditions. Then what we can say here is suppose that the inner product of f with g is given by the integral from a to b of f of x gx dx. Then what we can show is f of x equals the sum, n goes from 1 to infinity, cn xn. And it's just like we did a second ago. If I multiply both sides by another member of the eigenfunction set, and then I integrate both sides from a to b, because of the orthogonality that we've proved above, we've proved that this thing is equal to 0 unless n is equal to m. So rewriting this in terms of our inner products over here, this is the inner product of f of x with, I'll call it xn. I should say xm, but n is equal to m. And over here, all of the sum terms disappear except for one, and it's the nth term. And then this is xn inner product with itself. And so if you're solving for Cn, you end up getting that exact formula that we did just a second ago to solve for the Robin problem conditions. And this will always be the formula for the coefficients to that boundary value problem. Another way to write this, if you notice, you're taking the inner product in the denominator there, you're taking the inner product of an eigenfunction with itself, which is in terms of the norm. So another way that you'll often see this written is this is the norm squared of the eigenfunction, which is why this condition is posed. So here's what comes out of this. If we're solving the heat equation, one-dimensional heat equation, one-dimensional wave equation, on any interval, and we know that the initial condition is given to us by a function that's square integrable like this, then we know exactly what the eigenfunctions will look like. We know exactly what the eigenvalues will look like. Well, the eigenvalues could be numerically calculated, but we can find the eigenvalues. They will be real. And we can calculate the coefficient Cn by using this particular formula. It's not the last time we'll see this. This is actually going to be a recurring theme here for about the next 2 weeks. But this is all I wanted to go over with you today. So that wraps up the Robin problem. I think that's everything you need to be able to finish the homework for this week. So I think you're already good to go for homework set 5. There's really not anything else at this point. So quiz 5 is due March 27th, that's Friday, and homework set 5 is due March 29th, that's Sunday. So those are the two things that you need to be doing this week. Don't forget to turn in your literature reviews. All right, I'll see you again on Wednesday. Y'all have a good week. If you need to get a hold of me next week, email's great. You can come by during office hours, but I'll see you then. Bye.